Okay, so the next topic that I'll be discussing is turning effects of a force, and this is the last topic from the topics of forces. Um, Moving on, let's just first discuss what exactly is a turning effect of a force. So, basically, a turning effect of a force can also be called as the moment of a force, and moments occur when forces cause objects to rotate about some pivot. So previously we have studied different effects of forces like changing of shape when we studied Hooke's law, like movement, acceleration, free fall of an object because of acceleration due to gravity, that force. And similarly, we have studied a lot of other effects that a force can have on an object. But what happens when a force makes an object or anything rotate? Well, that is when it causes a moment. When a force causes an object to rotate, we call it a moment. So a moment is the turning effect of a force. So that's pretty intuitive that moments occur when forces cause objects to rotate about some pivot. Now we've not discussed the concept of pivots. Pivots are basically the point about which rotation occurs because uh, if you think about linear motion, we don't really necessarily need a reference point or a reference line along which that happens because we just have a path. However, when moments happen or when we're talking about turning effective forces, then it rotates about some point. It rotates about some specific pivot point and it makes an angle from that point. So that point is called pivot. You can think about a hinge. Let's just say we're taking an example of a door, right? So if you're opening a door, it rotates about what? It rotates about the hinges, it rotates about those points. So those hinges are the points. So, um, so the size of a moment depends upon the size of a force, the distance between force and the pivot. The moment of a force is given by the equation force multiplied with the perpendicular distance from the pivot. Moments have the units Newton centimeters or Newton meters depending on whether the distance is measured in meters and centimeters. If you're talking about SI units, then the units are going to be Newton meters. However, if we are thinking about if we have very less lengths or very small lengths, then it's better that we include um, centimeters, so Newton centimeters, and it can just be very different, whatever works. Kilonewtons, meter, kilo, Newton centimeters, Newton millimeters, whatever makes sense. So, um, the size of a moment. Okay, now basically we have like stated the main equation that is going to govern the moments, and that is that force multiplied with the perpendicular distance from the pivot gives us the moment. So let's just make it easier for ourselves and draw a. This is a door. It's it's like the side view of it, like the isometric view, if you know that means. And it's attached to these hinges. This is a hinge, and it's just like let's just say it's just attached to this holder, and this is another hinge, right? Okay, so now I come here, and I'm this person. I'm standing over here, and this is just a person, a random person who's standing over here like this, and they push the door, right? So they push it in this direction. Now they push it with some amount of force. Now that force multiplied by the distance, the perpendicular distance from the pivot gives us the moment. Now the perpendicular distance from the pivot of what? The perpendicular distance from the pivot to the line of action of force. To the line of action of force. To line of action. Oh my god, this action of force. So that's it. Now, if you look at it, it is basically like that this is a force, this is the line of action of force, and the perpendicular distance from the line of action of force to the door is going to be this one. And it doesn't really look perpendicular right now because I've shown the side view, but if you think about a door and you're just going straight perpendicular towards it and then you're pushing it. So basically the distance between the distance from your hands to the hinges is going to give you the perpendicular distance from the pivot that we need. So moving on. Okay, now what happens to a standing object as a horizontal force F is gradually increased? Assume the ground has a high friction. The ground has high friction, meaning that the object will not slide, instead, it will topple. So that basically means that the ground has high friction. So if there is an object that is standing on the ground and there is some force that is being applied to it, so that means that it cannot move. Why can it not move? Because in general situation, what should happen is that if you apply some horizontal force or some sliding force to an object, it should slide. But it will slide if the surface was more smooth or if it was more lubricated. But we are saying that that area has some friction, and so what happens is that if the ground has friction, now, that force is supposed to have some impact, like an impact that is caused by the force, the horizontal force that is being applied. So instead of sliding down the ramp or whatever this length is, what it does is that it topples over because it cannot move, it cannot move in this direction. So what it does is that it stucks at this point and then it topples over. So as F increases, the moment provided by the force, anti-clockwise moments, because it is going like this, and if you think about it, so that's anti-clockwise, and we are going to consider anti-clockwise moments as positive in this course, and the clockwise moments, which will be like this, as negative. This is just a convention and we are going to follow it. So as F increases, the moment provided by the force, anti-clockwise moment, becomes bigger than the moment of weight. Now the moment of weight was acting right here, right? So if initially it's pushed, so that's like the moment that is being caused, the moment like from here till here, because this is the pivot point. So when this becomes larger than that, so it topples over and it does not stay in equilibrium and it cannot stay its position. So examples involving moments. Some other examples involving moments include using a crowbar to prise open something, turning a tap on or closing it, opening or closing a door. So if you think about it, if you're turning a tap or you're turning it off, you're again using moments. Using a crowbar to prise open something, like if you're popping it up, then again you're using moments. So these are some daily examples that are like generally used in our daily life and are big examples of moments. So the principle of moments. Now this is a very, very, very important principle. Now what happens is that the law of moments, that is also called the law of Lever, states that when a body is in equilibrium, equilibrium means that an object is like at its equilibrium state, like it's at its peaceful state. If you think about it as conceptually, that it's at its safest, peaceful, static state. So when in a body, if you just that's not a scientific definition, but I'm just saying that in terms of concept. Like if you want to think about what an equilibrium is. So when a body is in equilibrium, the sum of clockwise moments about a point equals to the sum of anti-clockwise moments about the same point. So basically, I'm saying that it should not be rotating or should not have any net moment when it is in equilibrium. So there is no net moment on a body when it is in equilibrium. Now, this is an example that we're going to study, and in the above diagram, force F2 is supplying a clockwise moment, and force F1 and F3 are supplying anti-clockwise moments. So what happens is, If forces F1 and F3 are supplying anti-clockwise moments, if, hence we know that clockwise moment is equal to anti-clockwise moment. So I'm going to equate them. So F2 multiplied by D2 is equal to F1 multiplied by D1 plus F3 multiplied by D3. So that's basically me. So that so that's basically equating. So that's basically me equating the two clockwise and anti-clockwise moments together. Um, Now this is another example, and now there are two or three kinds of questions that can come in exam, and those are like, first one can be that you're asked to find the distance, the perpendicular distance of a force from an object, and from the pivot, and it is given that the lever or whatever that thing that is happening that is in the question is in equilibrium. So what you're going to do is just sum the clockwise moments and just equate them to the sum of anti-clockwise moments, and the variable that is missing is going to give you the answer. So sometimes it's going to be distance, sometimes it's going to be a force, sometimes it's going to be weight. Now do not forget, an important aspect is that when an object is given and its weight is not included in that and its weight is not included in that. Um, if there is an object and it is in equilibrium, but it's not balanced on its direct exact weight. Like if you have a meter rule, it's supposed to have its center of mass acting on its weight, its weight acting on its center of mass, which should be at 50 centimeters, but it does not do that. So what if you're balancing that at some other point, like at 25 centimeters. So it's important to see that even if there isn't an external force that is being applied at 50 centimeter mark, we should consider weight as a force that must be, that's like a given that is being applied, provided the pivot is not at its center of mass. So that's also a type of question. Now, what are levers? A lever is a device which can turn about a pivot. In a working lever, a force called the effort is used to overcome a resistant force called the load. A pivotal point is called the fulcrum. So, in basically, lever is like that there's one side pivot and the other side we are acting the lower. So that's basically lever. If you use a crowbar to move a heavy boulder in your hands, apply the effort at one end of the bar, and the load is the force exerted by the boulder on the other end. So that's another example of it. So this is the example. We're just going to be asked about the effort that is required. So that's just pretty simple. It's literally doing the same thing, principle of units. Now, initially we said that if a body is in equilibrium from the principle of moments, they they should be in equilibrium. They should have like equal clockwise and anti-clockwise moments. But equal anti-clockwise moments and clockwise movement does not mean that X ball is in equilibrium, but it is important for a body to have balanced turning effects if it is in equilibrium. So another condition of equilibrium is that the forces in one direction equal to the sum of forces in the opposite direction. That basically the moment as well as the sum of the turning effect as well as the moments they're equal to zero. So that's how we know the equilibrium. So I'll just read it again. Sometimes a number of parallel forces act on a body so that it is in equilibrium. We can say that the sum of forces in one direction equals to the sum of forces in the opposite direction. The law of moments must apply. If a resulting force acts on an object, it will start to move off in the direction of force, and if the resulting moment acts on an object, it will start to rotate. So basically, that means that we don't want any linear translation or any linear movement, and we don't want any rotation happening. So, in order to prevent those things happening, these two are the conditions of equilibrium, that there should be the sum of forces in one direction should be equal to the sum of forces in the opposite direction, and that the sum of moments, and that the law of moments must apply. So, For an object to be equilibrium, it must be experiencing no acceleration. This means that both net force and the net torque on an object must be zero. Here we'll be discussing the first condition, that the net force must be equal to zero. So if net is equal to zero, that means that F in x direction and F in y direction should be equal to zero if we're considering a two-dimensional state. The condition F net is equal to zero must be true for both static equilibrium when the object's velocity is zero and the dynamic equilibrium when the object is moving at a constant velocity. So this is an object, he's stationary, and this is a free body diagram that tells us that for an object to be stationary, there should be net force is equal to zero, so upward force is equal to downward forces, and y, that forces in y direction are to be accounting to zero, so that's how it is. The forces acting on and up to zero, both forces are vertical in the case. This is another case that is pretty simple again. Below the car is in dynamic equilibrium. Now what happens is that it's not static, it's moving, but its velocity is constant. So velocity is constant, that means no acceleration. No acceleration means no force. So that means if there's no force, so that means they're balanced. So it is moving, it is dynamic, but it is a dynamic equilibrium. So because it is moving at constant velocity, there are horizontal and vertical forces that are acting on it, but their net external force is equal to zero. So the applied force between the tires and the road is balanced by air, friction, weight, drag, and everything. So it just basically adds up to zero. For an object to be in static equilibrium, it has to have no direction, and while there is some motion, that motion can be constant. If an object in static equilibrium, both the net force and the net torque on the object must be zero. To understand what factors affect rotation, let us think about what happens when you open an ordinary door by rotating it on its hinge. The magnitude and direction at any point of application of force are incorporated into the definition of physical quantity called torque, the rotation equivalent of force. So it's the mere effectiveness of force in changing of acceleration and rotation. So if you think about linear motion, if you think about force that is causing something to move, then it's also similar that if an object is in angular movement, so if something is moving in angular motion, then that quantity is analogous to torque. So the rotational equivalent of a force is basically torque. That is about it, and there are just some examples that should be done